Howdy and welcome back. So some additional terminology. This video should be short and sweet and to the point. So I wanted to introduce this concept of a connected graph, which is simply a graph can be labeled as connected if there's a path from every vertex to every other vertex in the graph. Contrast the example provided here on the left with that on the right, where a graph can be considered not connected if we're unable to access each of its the vertex from every other vertex. So if you notice here on the left, everything is accessible from X1. We can get to literally any other vertex presenting within this graph by simply navigating through it, following the edges. We can end up at X2, X4, X3, X6, or X5. However, contrast this with the non-connected graph on the right here. From X1, we can only access a subset of the vertices presenting in our graph, X2, X4, and X5. X3 and X6 are not accessible. And we can see here that this essentially forms two sets of connected components where these vertexes are all connected to one another in the first set that I labeled there. And then this second set where we have X3 and X6 connected through an undirected edge. Cool. Erase that up. So moving on to the next kind of term I want to introduce is this idea of an acyclic graph. It's simply going to be a graph with no cycles, and we'll define cycles as we did in the previous lesson. Now here's where I guess kind of graph meets tree, the topic of a previous week's lesson, the trees. We can say that or view a tree as an acyclic connected graph. So if we kind of look at our representation, here of this acyclic graph, it really isn't that much different from that of the tree presenting over here of this particular binary tree. Anyhow, there are some differences in terms of the number of children, I guess we could say, in the graph, and we are using some different terminology where when we were discussing trees, we were talking about different nodes connecting to one another, parents, children, etc. When we've been talking about graphs, we've just been saying, here's all these this set of vertexes, and they're connected to one another to show some sort of relationship through and edge. Okay, so let's go ahead and kind of introduce this idea of paths through a graph. So a path in a graph is simply going to be a sequence of vertices that we're going to visit through some sort of connected edges. For instance, one path through a graph could be the traversal of going from X1 to X2 to X4 to X6 along the edges X1, X2, X2, X4, X4, X6. And we can say that this is going to be a path through our graph. We can specify the length of a path or a cycle by the number of edges that are traversed over the course of that path. The path from X1 to X2 to X4 to X6 is going to be of length 3 because there are 1, 2, 3 edges that we traversed. Now, there is an idea of a subgraph. So a subgraph is going to be a subset of a graph's edges and associated vertexes. A subgraph can constitute a graph in its own right. So if we look here, I've simply extracted the nodes and edges associated with the path on the previous slide to create a subgraph denoting that path. Finally, almost finally, one of the additional terms that I would like to introduce is this idea of the density of a graph, which is going to be defined as the proportion of possible pairs of vertices that are connected through edges. We're going to say that a sparse graph has a relatively few possible edges present out of the total number of edges that would otherwise be possible, contrasted against a dense graph, which has a relatively few of the possible edges missing. And then to go ahead and close out this video, I just want to introduce this kind of concept of adjacency. If a vertex V is adjacent to another vertex W, then we will say there exists an edge between V and W to make them adjacent to one another. So with that, let's go ahead and transition into some vertex naming and edge notation.